This is a lecture that I give only with some trepidation. This is the lecture in which we don't learn anything new about the universe, about dark matter or dark energy. We just take something that we've already been saying about dark energy and try to really understand it at a deeper level. This is the lecture that you will not ordinarily hear about in speeches about dark energy in the accelerating universe, because it's easier to say some words that sound like they make sense and then quickly move on to the next thing. So the purpose of this lecture is to go deeply into those words that sound like they make sense, convince you that they shouldn't have made sense in the first place, but if you think about it hard enough, they begin to make sense again. So I'm not sure whether this is even the right thing to do, but I think it's valuable enough that we really understand what is going on when we start talking about dark energy. What we've said about dark energy is that it has two very crucial properties. One is that it is smoothly distributed through space. The same amount of dark energy is right here in this cubic centimeter as somewhere way in between galaxies and clusters very far away. At least the data are telling us there's not substantially more dark energy inside galaxies and clusters than in between the galaxies and clusters. That kind of makes sense. Had there been more dark energy inside a cluster, we would have noticed. It would have felt its gravitational field in the dynamics of the stuff inside the cluster. The other part of dark energy is that it's persistent. The energy density in the dark energy is approximately constant as the universe expands. What that's telling us is that the dark energy is not made of some kind of particles that are becoming more and more dilute as the universe gets bigger. If that were the case, the energy would be going down. There'd be fewer particles per cubic centimeter. Whatever the dark energy is, it's something that stays the same as the universe gets bigger. So that's something we'll have to get into. What are the possible candidates for stuff that could have a persistent energy density? But today what I want to talk about is instead the idea that if you have a persistent energy density, it makes the universe accelerate. Why is it that if the density of stuff doesn't go down, the manifestation of that in observable quantities, that the universe expands faster and faster? In fact, there are two different ways to explain this, and they're just two different sets of words that we attach to the same set of equations. The truth is that this project of attaching words to equations is just because as human beings, we like to have some intuitive grasp on what is going on. The equations themselves are completely unambiguous. There's no question about what does happen. The equations are telling you absolutely once and for all that if you have an energy density which doesn't change as the universe expands, it will make the universe accelerate. It's perfectly clear at the level of the equations themselves. But we would like more than that. We would like to go beyond just being able to write some equations down to really have a deeper understanding of why it is like that. So these are our attempts to attach words, to attach concepts that make sense to us onto those equations. Sometimes these attempts are going to necessarily be incomplete or necessarily be fuzzy in some way. They will make a certain amount of sense to us, but they are not nearly as rigorous as the equations themselves. So I'm going to give you two different explanations for why persistent dark energy makes the universe accelerate. Neither one is wrong, but you may find one explanation more compelling than the other one. That's perfectly okay. That's up to you. The first explanation you will often hear is the following. I'll give you the whole thing, and then we'll sort of unpack it and see why it makes sense. The explanation says, dark energy has a negative pressure. In addition to positive energy density, there's also a pressure, but the pressure is a negative number. The thing that gravity responds to, according to Einstein, is a combination of energy density and pressure, and that combination added up can be a negative number if the pressure is sufficiently negative. Even if you have a positive energy density, you can still get a negative gravitational effect in the presence of negative pressure. That's what happens when you have dark energy, and that's why dark energy makes the things in the universe move apart faster and faster. It's almost like anti-gravity pushing things apart. So you can decide for yourself whether or not that set of words I just said made sense. What I want to do is to go into them more deeply, try to understand why what we think of as dark energy would have a negative pressure, and why something with negative pressure would make the universe accelerate. Before we get there, we need to understand a little bit about the very notion of conservation of energy. Conservation of energy is one of the most cherished concepts in physics, going all the way back to Galileo, if not earlier. We want to know how it works in the context of relativity, which is, after all, a different theory than classical Newtonian mechanics. There's no necessary logical reason that once we understand the laws of physics better, it needs to continue to be the case that our old cherished notions are still true. In the context of relativity, the way that conservation of energy is manifested is different. In fact, you could say, without being incorrect, that the energy in general relativity is just not conserved. And I will try to make sense of that statement. You may have noticed that the energy of the universe seems not to be conserved in the presence of dark energy. On the one hand, I've said that dark energy has an energy per cubic centimeter that is approximately constant, maybe exactly constant. If the dark energy is vacuum energy, it is a strictly, absolutely fixed amount of energy per every cubic centimeter. On the other hand, the universe is getting bigger. The universe is expanding. There are more and more cubic centimeters in space as the universe expands. Therefore, isn't it true that the total amount of energy in the universe is going up? Doesn't this mean that the energy is not conserved? The amount of energy is growing. So the answer is yes, the energy is growing, it is not conserved. And then you're supposed to say, isn't that bad? Doesn't that violate my cherished notions of conservation of energy? The answer is, it is not bad. It actually makes perfect sense within the context of general relativity. So to convince you of this, let me point out that even without dark energy, it is still the case that energy is not conserved in an expanding universe. Just think about an expanding universe that is more conventional. It has nothing in it but photons and ordinary matter particles, stuff that we certainly know exists. So in a given region of the universe, this region is expanding. There's a number of particles in that region, and the number of particles stays the same as the universe expands. Now, there's two different regimes for the kinds of particles we can consider. There are matter particles. Matter particles move slowly compared to the speed of light. And there are radiation particles. Radiation particles move at or close to the speed of light. So in each one of those cases, you get a different formula, a different idea of what the energy per particle is. For a matter particle, it's E equals mc squared. For a slowly moving particle, most of the energy per particle is in its rest mass. What that means is that as the universe expands, the energy in each individual matter particle stays constant. So because this region of space is expanding, the total number of particles in that region is constant, the total energy in matter in that region will remain fixed as the universe expands, just as you might hope it would do. On the other hand, consider the energy in radiation in that same box. There, you have a fixed number of radiation particles. The number of particles isn't changing, but the energy per particle is going down. The effect of the stretching of space-time is to increase the wavelength of every individual photon. The kinetic energy, if you like, of the radiation particles is diminishing because of the expansion of the universe. Therefore, if you add up the total amount of energy contained in radiation in that box as it expands, you don't get a constant. You get a number that decreases as the universe expands. So there's actually an amusing psychological effect going on here. With dark energy, as the universe expands, the total energy is not conserved because it's going up, and that bothers people. With radiation, as the universe expands, the total energy is not conserved because it's going down. That doesn't seem to bother people as much. But from the equation point of view, both of those are exactly equally good or bad. If energy is conserved, the energy should not change, which means it should not go up or go down. So the truth is that in an expanding universe, or in general relativity more generally, there's no reason for the total energy of stuff in the universe to be conserved. By stuff, I mean not space-time, I mean the substances that are in space-time, whether they are dark energy, dark matter, ordinary matter, radiation, or what have you. If you were to dig down into the classical laws of physics, as Isaac Newton proposed them, there is a reason why energy is conserved. The deep reason why energy is conserved was actually first understood by a mathematician named Emmy Noether. She figured out something called Noether's theorem, which says that if there is a symmetry of nature, associated with every symmetry is a conserved quantity. Something that is a symmetry of nature implies there is some number you can calculate that never changes. It doesn't quite go the other way. Just because something is a conserved quantity doesn't mean it comes from a symmetry, but it is very often the case. Energy, for example, is conserved because of a certain symmetry of nature. What symmetry of nature is it? It is time, translation, invariance. It's the statement that the laws of physics and the playground on which physics happens don't change as time goes on. That is a true statement in Newtonian mechanics. In Isaac Newton's universe, space and time are fixed and constant. Space does not change. Nothing happens to space. And the laws of physics also remain unchanged. Therefore, in Newtonian mechanics, you can go through a set of equations which lead you to the conclusion that energy must be conserved. But general relativity works differently. General relativity allows space and time to be dynamical. In particular, we know that in cosmology, the universe is expanding. In other words, the playground, the stage on which physics plays itself out, is not invariant under time. The universe in the past was different than the universe in the future. And therefore, the deep reason we had to believe in energy conservation is no longer true. It is not deep down a surprise that in an expanding universe, energy is no longer conserved. Nevertheless, there is still an understanding of what happens. It's not that chaos has broken loose because the universe is expanding. There used to be, in Newtonian mechanics, a rule that says the total energy is constant. Now, in general relativity, there is a new rule, but there's still a rule. The new rule says how the energy changes as the universe expands. If you tell me exactly how the universe is expanding, I can tell you exactly how the energy will change in response to that. Fortunately, there's actually a very easy way to understand this rule in terms of a much more mundane system, namely a piston. A piston in exactly the same sense in which you have pistons in your car, in the engine that is turning the energy in your gasoline to the kinetic energy of your car. In a piston, we imagine the simplest possible case in which we have a piston pushing in to some substance, and we're changing the volume of that substance by pushing the piston in or by pulling it out. Now, if you have ordinary gas inside, by gas I mean the state of matter, not gasoline, inside your piston, if you have a gas like air or anything like that, it takes energy to push it in. You can get energy by allowing it to come out. We say that the gas in the piston has a positive amount of pressure. The gas in the piston is pushing on the piston, and therefore if we just let it go, we could hook it up to a little engine, which is what you actually do inside your car, and you're getting energy out of the piston by allowing it to expand. That's what a positive pressure does. A positive pressure says you can extract energy by increasing the volume. That's exactly what happens to a gas, for example, made of photons. In the universe, we can imagine applying the phrase gas to a collection of photons bouncing off the walls of our little piston. Photons are going to bounce into the piston. They're going to exert a force on it. That force is what we perceive as the pressure. So the photons in the piston will push on the piston. We can extract energy by increasing the volume. That's just what the universe does. The universe, by expanding, takes energy away from those photons. If instead, inside the piston, we had a bunch of particles that weren't moving, particles that were motionless like matter particles, then we wouldn't get any energy by pulling on the piston. And again, that's exactly what happens in the universe. The universe expands, matter particles don't lose any energy in that way. So positive pressure means that as we increase the volume, we take energy away. Therefore, you might guess that what negative pressure means is that we increase the volume, we put energy in. That's what a negative pressure is. So if you try to imagine some physical system inside the piston that would have a negative pressure, it's something that when you pull on the piston, the system pulls back. For example, we could imagine a complicated system of rubber bands or springs inside the piston that were tied to the walls. So if there's a rubber band that goes from one end of the piston to the part that we're pulling out, when we pull, it will pull back on us. That is a negative pressure, or equivalently, it's called a tension. A rubber band has tension. It takes energy to make it bigger. It's not giving us energy when we make it bigger. So now let's think about, what if we had a piston full of dark energy? This is a special kind of non-physical thought experiment. We're imagining we have a piston with dark energy inside and no dark energy outside. Outside we just have zero energy everywhere. Inside we have a system with the property that the amount of energy in every cubic centimeter is a constant. So what happens? If we take that piston and we try to expand it, we are increasing the volume inside the piston. The energy per cubic centimeter inside remains constant, so the total amount of energy inside the piston goes up. In other words, we have to put energy into the system to pull out our piston. That is, if it makes sense, the proof that dark energy has a negative pressure. Dark energy is a system that requires energy for you to make it bigger. You need to put energy into the system somehow. Since negative pressure is sometimes called tension, I have occasionally semi-seriously argued that dark energy is not a good name for dark energy. Everything in the universe has energy, and there's lots of things that are dark. So the essence of dark energy is not really correctly described by calling it dark energy. The important things about dark energy are that it is smoothly distributed and that it has a negative pressure or a tension. So I propose that we call dark energy smooth tension, which is both more accurate and kind of sexier than dark energy. It did not catch on, though. I was too late in coming up with this. So everything hangs together in this picture of how energy works. If you have an object or a physical system that has tension, that has negative pressure, then when you expand the volume that it takes up, you're putting energy into it. So contrary-wise, if you have a system whose energy remains constant, you know that it has a negative pressure. However, in the case of the piston, there was an external agent. There was an outside, without any dark energy, someone pulling on it. There is no equivalent in the case of the actual universe. There is nothing outside the universe pulling on it or pushing on it. The universe is just evolving in accordance with Einstein's equations. So the analogy breaks down a little bit there. If you counted for the piston, the energy inside the piston and the energy of the person pulling on it or pushing on it, that total energy would be conserved. As far as we know, according to our current theories anyway, there isn't anything outside pushing or pulling on the universe. It's just that the universe has an energy of its own that is not conserved. So we have to learn to deal with that. Now let's see if that helps us understand why the universe is accelerating. Let's grant that dark energy is associated with negative pressure. Dark energy is something that it takes energy to make the volume bigger and bigger. So what? Well, we have to go back to Einstein's equation, which is telling us how the curvature of space-time responds to stuff. Einstein's equation has a left-hand side involving the curvature of space and time, and it has a right-hand side involving what we call the energy-momentum tensor. In other words, Einstein's equation of general relativity involves a unification of different concepts, just like special relativity does. Remember that special relativity was inspired by Maxwell's theory of electromagnetism, which unified our description of electricity and our description of magnetism. Special relativity itself unified our idea of space with our idea of time into one notion of space-time. General relativity unifies the stuff that causes a gravitational field. It used to be, according to Isaac Newton, the stuff that caused gravity was mass. So Einstein says in special relativity that mass is a form of energy. In general relativity, he says the stuff that causes gravity is every form of energy. It's not just mass. It's momentum, it's pressure, it's strain, it's a whole bunch of different ways in which energy can manifest itself. So the thing that appears on the right-hand side of Einstein's equation is not just the energy density, it's also the pressure. So if you work through some math, which we can't quite do right now, you find that there's a rough guideline that says that on some cubic centimeter of space, the thing that makes it expand or contract, according to gravity, is not just the energy density, it's a sum of energy density and pressure. The particular sum that it is the energy density plus 3 times the pressure. Why is it 3? It turns out because there are 3 dimensions of space. If you lived in a universe that had 5 dimensions of space, the force of gravity on a cubic centimeter would be the energy density plus 5 times the pressure. So what that 3 means is that if you have a pressure that is equal but opposite to the energy density, then it wins in that formula because there's a 3 multiplying the amount of the pressure. You have an energy density which is positive, a pressure which is negative and comparable to the energy density, then the energy plus 3 times the pressure will be a negative number. That means that instead of pulling space together, like you might guess, a sufficiently negative pressure pushes space apart. It makes the universe accelerate. It's kind of like anti-gravity in the sense that things move apart from each other under the influence of gravity rather than coming together. So I could probably stop there and you would be willing to buy it. Let me just point out a tiny little sleight of hand that happened in that argument. It's not a lie, it's not a misleading you, but there's something that goes by very quickly which is worth paying attention to. The gravitational effect of the pressure is what is being talked about here. A negative pressure, remember, inside the piston, what does a negative pressure do? It pulls on the piston. A negative pressure wants the piston to decrease the volume because that saves energy. But what we're saying here is that a negative pressure in the universe makes the universe accelerate. How did that happen? What just went on? What went on is, if there is pressure in every direction, nothing happens. There's no force of the air pressure in this room on my hand because it's acting equally and oppositely on both sides of my hand. I don't feel any net force due to the pressure of the air in this room, even though the amount of pressure is 15 pounds per square inch. If I only had that pressure on one side, it would be pushing my hand over like that. The same thing happens with the negative pressure of the dark energy in the universe. It's exactly the same at every point in every direction, and therefore you feel precisely nothing from the direct impact of the negative pressure of the dark energy. On the other hand, there's a gravitational effect. There's an indirect influence of the negative pressure due to its impact on the curvature of space-time, and that effect is to make space expand faster and faster. So all of those words are true, they hang together, they make sense, but you need to buy into the claims that dark energy has negative pressure, that there's a certain formula for the expansion of space, which is the energy density plus 3 times the pressure, and the fact that the pressure itself exerts no net direct effect. Therefore, I can't resist giving you my favorite explanation for exactly the same phenomenon. Why does a constant energy density make the universe accelerate? I will explain why without referring to the concept of a negative pressure even once. So here is the other explanation, which is equally good, but I like it better. The explanation says that dark energy is persistent. The energy density does not go away, it remains constant as the universe expands. Therefore, the energy density gives a constant, persistent impulse to the expansion of the universe. That persistent impulse in every cubic centimeter of space manifests itself as acceleration. That's more or less the set of words I said already before. Let me unpack it a little bit more so you understand the deep meaning behind that chain of logic. We need to go back to the Friedmann equation, the equation in cosmology that relates the curvature of space-time to the energy density. But now, to save ourselves a little bit of conceptual work, we will set the spatial curvature equal to 0. We have data from the microwave background that says the spatial curvature is 0, so it's good enough to look at the Friedmann equation without the spatial curvature term. In that case, we get a very simple relationship. The energy density is proportional to the expansion rate squared. The expansion rate, of course, is measured by the Hubble constant, the Hubble parameter, which relates the velocity that you observe in a galaxy to the distance that it is from you. So if the universe had nothing in it except for dark energy, just to do a simple thought experiment, what would happen? We would have an energy density that was constant. If you have a constant energy density, and the energy density is proportional to the Hubble parameter squared, then the Hubble parameter is constant. In conventional cosmology, when matter and radiation are important in the early universe, the Hubble parameter was much bigger at earlier times than it is today. In this fake toy universe we're discussing just for the moment, with no spatial curvature, no matter, and no radiation, nothing but dark energy, you would have a Hubble parameter that was truly constant, that never changed as the universe expanded. So you're allowed to ask, wait a minute, I thought you just told me that the dark energy made the universe accelerate. How can it be that a universe where the Hubble parameter is constant is accelerating? In an accelerating universe, shouldn't the expansion rate be going up? And the answer is no, and this is just one of those miracles of non-Euclidean geometry that manifests itself in general relativity. A constant expansion rate corresponds to an accelerating universe. And that's because the expansion rate is not a velocity. The expansion rate, the Hubble constant, is not giving you directly the velocity of a galaxy. It's telling you if you know the distance to a galaxy, what would the velocity be? We return to the Hubble law, Hubble's very simple equation, which says that the velocity of a distant galaxy is the Hubble constant times the distance. So the Hubble constant relates all sorts of different galaxies to the velocities you observe. Now ask what happens, according to Hubble's law, if the Hubble constant is strictly constant, if it's not changing. Look at one galaxy and let the universe expand. Well, the velocity you observe is the distance to that galaxy times the Hubble constant, but as the universe expands, the distance is increasing. And therefore, if the Hubble constant doesn't change, the velocity that we perceive will also increase. That's what we really mean when we say the universe is accelerating. We say that if you look at one galaxy and follow its velocity as a function of time, that velocity goes up. The galaxy moves away from you faster and faster. That's what it means to live in an accelerating universe. In a decelerating universe, in a universe that only had matter and radiation in it, the distance would increase, but the Hubble parameter would decrease even faster. That's why you would see the velocity of a distant galaxy decrease in a decelerating universe. The statement that the universe is accelerating is equivalent to the statement that the Hubble parameter is either constant or decreasing more slowly than the distance is increasing. That's what it means to accelerate. Let me say exactly the same thing in a different set of words. One way of thinking about what the Hubble parameter is telling you is how long it takes for the universe to increase in size by some fixed number. So let's say the Hubble parameter is telling you it takes 10 billion years for the universe to double in size. And let's furthermore say that the Hubble parameter is constant. This is more or less what we have in our current universe. So that's saying every 10 billion years the universe doubles in size. What that means is if we take two galaxies that are 1 billion light years apart, we wait 10 billion years, they will now be 2 billion light years apart. Another 10 billion years from now, they will be 4 billion light years apart. And another 10 billion years from now, they will be 8 billion light years apart. It's just they told two friends and they told two friends. These galaxies move apart at a velocity, an apparent velocity, which is ever increasing. And the reason why is that every cubic centimeter of space is expanding at a constant rate. A constant expansion rate of space plus an increasing amount of space in between the galaxies leads to an acceleration of the two galaxies away from each other. That is my favorite explanation for why dark energy makes the universe accelerate. You don't need to go through the intermediary of a negative pressure, which is kind of a difficult to grasp idea all by itself. You can just say that what energy does is contribute to the curvature of space-time. In a flat universe, what that means is that energy contributes to the expansion rate of space-time. And if that contribution doesn't go away, the expansion rate of space-time will persist. If we lived in a universe without dark energy, a universe with only ordinary matter and radiation, the far future of the universe is one in which it expands ever more slowly, it gets emptier and emptier, and it approaches exactly the situation you would have if there was no stuff in the universe, if you were not expanding whatsoever, if you were in a static, unexpanding, empty space-time. But with dark energy, with stuff that doesn't go away, there's always something that is making the universe expand with this constant magnitude. The manifestation of that to us is that we see individual galaxies moving away faster and faster. So hopefully, all of that now makes perfect intuitive sense to you, except we're still left with the question, what is this dark energy stuff? So with the next lecture, I'll be wearing a different tie, and we will start thinking seriously about different candidates for what the dark energy might be.